Okay, so hello everyone. My name is Javier Berrueco. I'm developing my thesis at INTA, the Natural Institute for Space Technology here in Spain. Here in Spain, sorry. My supervisors are Rodrigo Castellanos and Esther Andres Perez from INTA. And yeah, aerodynamic shape optimization using reinforcement learning is the thesis title. Does it make sense? Well, if you think it does not, I'm going to convince you that it really does. Okay. I will talk about the two core elements of my thesis, which are ASO and RL, the roadmap, and the progress I've made so far. So let's start by defining aerodynamic shape optimization, which at the core, it is the process of modifying a geometry to minimize its aerodynamic drag. This simple task can translate into savings of billions of dollars, of thousands of tons of fuel, or thousands of tons of emissions. Every ASO framework is built in three core elements. The first one is the geometry parameterization. We have to create shapes of geometries with the few variables as possible while maintaining, okay. Okay, yeah. While maintaining enough flexibility to create complex shapes. The second pillar is the aerodynamic evaluation. This is the most expensive stage of the dynamic shape optimization process, and is the main bottleneck because we can use very highly accurate evaluations, but it has its cons too also. And finally, the optimization algorithm is the engines that drives the entire process, constantly varying the variables to create new shapes and achieve the best one possible. So now let's look at the current state of the art in the ASO. The three biggest hurdles we face are the extreme computational cost of simulations, the curse of dimensionality when parameterizing complex shapes, and the multimodality and non-convexity nature of these design spaces. To tackle this, the current industry standard is the gradient-based approach, the adjoint method coupled with CFD evaluation that is highly efficient for high-dimensional problems. On the other hand, gradient-free methods like heuristic algorithms or genetic algorithms are excellent at navigating these non-convex and complex design spaces, but their trial and error approach makes them really expensive to use with high fidelity CFD, for example. And this is exactly why machine learning is becoming essential. ML acts as a bridge, reducing dimensionality. It can reduce dimensionality, and it can also bypass those expensive high-fidelity CFD evaluations, accelerating the entire optimization cycle. Despite its potential impact, a recent review points out that ASO exhibits the lowest growth rate between the fluids and AI intersection, suggesting that it might be relatively mature or facing technical bottlenecks. Let's look at how reinforcement learning is currently applied to aerodynamic optimization. Researchers use primarily stable algorithms which excel at handling the continuous nonlinear variables required to modify shapes. The optimization is framed as a Markov decision process in which the agent takes actions that modifies the shapes directly or incrementally, and then receives a reward based on the, for example, lift-to-direct ratio, and also they are informed with some observation of the environment which we call state. Since RL requires thousands of evaluations and episodes to learn, running high fidelity CFD to train an agent is something you really want to avoid. In my case, if I want to end my PhD eventually. So the actual standard is the transfer learning that in which agents are pre-trained on extremely fast surrogate models and then fine-tuned in complete CFD solvers. Moreover, standard agents rely on geometric states, which making them overfit. By guiding the agent with physical flow features, we can enable zero-shot generalization to different flight conditions. All this brings us to the core motivation of my thesis. First, we have mentioned ASO is critical in almost any transport industry. Second, we have discussed the limitation of traditional ASO methods and the need of new ones. And third, we have reviewed the pros and cons of using RL for ASO. And also, the lack of generalizability for the reinforcement learning in this problem. So this leads directly to my research question. How can a deep reinforcement learning framework be developed to enable the creation of aerodynamic shape optimization strategies that generalize to unseen flight condition, zero shot, without requiring retraining? Moving on to the overall roadmap of my thesis, in 2025, I laid the groundwork by building a conventional ASO framework and tailoring it to propeller blade shape optimization using a hybrid genetic algorithm. And currently, in 2026, my main focus is upgrading this system into RL-driven framework, specifically targeting airfoil optimization. Looking ahead to 2027, I plan to further validate our core scientific hypothesis by applying the RL framework to a different problem, probably the propeller blade shape optimization that we have already faced. And finally, in 2028, hopefully, it will be fully dedicated to concluding any open topics and structuring the manuscript and defending the thesis. Now, I'd like to share with you my progress. Last year, as I've said, I started my PhD building this standard ASO framework, tailoring it to propeller blade shape optimization. The main objective that is still a basis in my current work is to optimize using low-cost physics, neural surrogate models, and efficient algorithms. In this case, a hybrid genetic algorithm which was HIGO. Why? Because we can leverage from ML at the early stages of the preliminary design process, where the genetic algorithms are preferred due to their exploration capabilities. The objective of the optimization was the small UAV propeller blade shapes. And to do this, I built my framework. The propellers are generated from 48 design variables distributed in 4 control sections and then propagated to generate the rest of the blade. And the propeller is evaluated using the blade element momentum theory. The airfoil evaluation strategy needed for the blade element momentum theory was hybridized. It uses 2 solvers, which was SFoil, a panel method code, and neural foil, a physics-informed neural network that solves some SFoil issues in terms of conversions and time. The hybridization was made in terms of balancing time and precision. Okay.
Javier, sorry to interrupt, but you have consumed your 10 minutes
Okay.
right now. So please finalize your talk.
Okay.
Go to the conclusions or...
Yeah, for sure. So the results were really promising. The main claim here was that we really save more than 100 times in optimization time in comparison with SFOIL and even more with runs. I presented this work at Eurogene in September last year, okay? And my work is included in the conference proceeding, which will be published this June. And right now I'm building my environment with RL, reproducing an existing methodology, okay? And exploring and tailoring it to solve the initial question that I presented some slides ago. And just to share with you some other activities I enrolled that I think that are really useful. Some courses of good or the best scientific practices to talk about ethics, publication results, projects, fundings, and also some mentoring programs that help you to look for career advice or also to discuss about ethics, results, publications. And that's conclude my presentation. Thank you to INTA, my advisors, and you for your attention. Sorry for the time. And I will be happy to receive any feedback, comments, or answer your questions. Thank you.
Okay, thank you.